This week, we're going to be talking about the chi-squared test of independence and the non-parametric tests. So far in this class, we have talked about parametric tests, and these are statistical procedures that had the assumption of continuous variables were being normally distributed. Non-parametric tests, on the other hand, are used when this assumption cannot be made because either the variables are not continuous, i.e. either ordinal or nominal, or the variables are highly skewed, even if they are continuous. So non-parametric tests, they're not as commonly used because they have lower statistical power, but they're useful in real-world settings. We don't always have samples that have variables that are measured on a ratio or interval scales, or even if they are, they might not be normally distributed. And so we could use non-parametric tests to determine if there is significance. So the chi-squared test of independence is used when there's two categorical or nominal variables, i.e. college major and gender, and it's used to test whether there is a statistical association between these two categorical variables. So are college major and gender independent of each other, or does one impact the other? Essentially, this test determines whether cases in a sample fall into categories in proportions proposed to the null hypothesis, or by chance. So we again use the five-step hypothesis to test this. We state our null and our alternative. Our null hypothesis is that in the general population, there's no association between the two categorical variables, A and B. Alternatively, there is a statistically significant relationship in the general population between the two categorical variables, A and B. We set our alpha at 0.05. We compute our chi-squared test statistics. We make our decision and report our results. So let's take this example. Suppose we want to know whether the major that college students choose is related to their gender. So we conduct our study. We randomly select 75 students from the University of Memphis, and this is the data that we've got. So we can see that there are 25 business majors, 25 science majors, and 25 nursing majors. In business, there's 17 men and 8 women. In science, there's 11 men and 14 women. In nursing, there's 9 men and 16 women. Down at the end, we can see that we have a total of 37 men and 38 women in our sample, and we have 25 of each of the majors. This table is called a contingency table, and it is what we are going to test compared to what we would expect if gender and major were not associated at all. So, our null hypothesis. In the general college population, there is no association between gender and choice of college major. Alternatively, in the general college population, choice of college major is dependent upon gender. There is a formula that you can use to calculate this. And essentially what we're doing is we're comparing our actual values in the pink, what we found, with the expected values if there was no association between gender and college major. So if there's no association between what your gender is and what major you select, we would normally expect, given a sample of 75 students, to find 12 and a third men selecting business, 12.33 selecting science, and 12.33 selecting nursing. And if there's no association between gender and college major, we'd expect 12.66 women to fall into business, science, and nursing equally. However, this is not the case, right? We can see that we had 17 men in business, 11 in science, and 9 in nursing. So what we want to do is we want to know, is there a significant relationship between gender and college major? So we will go into SPSS and test this. So in SPSS, we can see that we have our participant ID, and we have 75 participants. We have the 3 majors, nursing, science, and business, and the 2 genders for man and woman. So what we'll do in order to run our chi-squared is we'll go to Analyze, Descriptive Statistics, Crosstab. We'll move our gender into our rows and major choice into the columns, just like we had in our contingency table. We want to click Statistics and then chi-squared and hit OK. and then click OK. In our output, we get 3 tables: our case processing summary, which is our descriptive statistics, and this is going to tell us our sample size, which was 75. The next thing we get was the gender times major cross tabulation. This is essentially our contingency table that was in pink before. And then we get our chi-squared test, and this is going to be what we're looking at to determine if we have a significant association between the two categorical variables. So we can see in the Pearson's chi-square that our chi-square value is 5.548 or 5.55 if you round, with 2 degrees of freedom and a p-value of 0.062. So we'll write this up. A chi-squared test of independence was conducted to determine whether there was an association between gender and college major in the general college population. The results of the analysis showed that choice of college major is not dependent on gender. There's no significant relationship. Chi-squared, parentheses 2 for degrees of freedom, equals 5.55, p equals 0.062. We have some other non-parametric tests that are commonly used. The first is the Mann-Whitney U-test. In all of these slides, there is a purple box that will tell you how to do this in SPSS. However, you do not have to do this. The Mann-Whitney U-test is the equivalent of the independent samples t-test or two-sample t-test. So we would use an independent sample t-test when our independent variable has 2 levels, tutored or not tutored, and the dependent variable is continuous, like final exam score, 0 to 100. We're essentially comparing the means of the groups to each other. The Mann-Whitney U-test, our non-parametric version, is conducted if the dependent variable is ordinal, okay? So you know if it is first, second, third, fourth, fifth. So we have our independent variable, 2 levels, tutored and not tutored, and our dependent variable is class ranking based on your final exam. So first place, second place, third place, okay? And under the purple is how you would write it up. We have our Kershaw-Wallace test. This is the non-parametric equivalent of a one-way ANOVA. A one-way ANOVA is a parametric test where our independent variable has more than 2 levels, tutored for 2 months, tutored for 1 month, or not tutored, and our dependent variable is continuous. The Kershaw-Wallace test is used if the dependent variable is ordinal or the dependent variable is highly skewed. So our independent variable, our grouping variable, has more than 2 levels, and our dependent variable is ordinal. The Wilcoxon-signed ranks test is the non-parametric equivalent of the paired samples t-test. So in the paired samples t-test, we had 2 independent levels that were related to each other, such as pre-test or post-test, or 5th and 6th grade achievement score, and our dependent variable was continuous. The Wilcoxon-signed ranks test is conducted similarly if our dependent variable is ordinal or it's highly skewed. And finally, the Friedman's test. This is the non-parametric equivalent of a repeated measures ANOVA, which you'll cover in Stats 2 if you take that. A repeated measures ANOVA is when your independent variable has more than 2 levels and they're related to each other, so time 1, time 2, and time 3. So maybe 4th grade achievement, 5th grade achievement, and 6th grade achievement, so 4th, 5th, and 6th grade, and the dependent variable is continuous. The Friedman's test, the non-parametric equivalent, is used when our dependent variable is ordinal or it's continuous.